Thanks, Martin. And next up is Jeff Frankhauser, and he'll be giving a talk on statmoxing.
Thank you. So my name is Jeff Frankhauser. I'm an engineer for XKL, and we design optical networking technology. Our company was founded 15 years ago by the co-founder of Cisco Systems, and this is his next company. Next slide, please. Okay. So when we look at the optical networking world, we see explosive amount of band growth in the amount of applications, the distances, the new protocols coming on board, the torrent of information that will be coming from the Internet of Things. And a lot of networks have gone from 10 gig to 100 gig to 200 gig to on, up to multi-terabits. With the amount of information coming over the next many years, these networks are actually going to continue to be constrained. You have business to business, you have machine to machine, all those things are taking place. And you have the gains today are being made by increasing spectral efficiency. We have the modulation schemes of DPQPSK, QAM8, QAM16, QAM32. And all those add spectral efficiency by the ability to increase your bandwidth by exponentially by tenfold. However, within that spectral efficiency, in some cases, depending on the protocol, you're still at 50% of your transport rate. And so we feel that solution lies within the ability to provide statistical multiplexing in the optical plane at layer 1 and do excessive bandwidth management without dropping a lot of packets and increase spectral efficiency by 100% without all the modulation schemes. They work very, very well, and we increase them or we add them to our product set as well. However, there's a point when you're moving so much data that you have to decrease the distances between your amplifications, so your economies of scale begin to fail long term. So we've addressed that through integrated statistical multiplexing. It's been around for a long time. Most of the people that are in routers and switches know the technology quite well. So at layer 1, we can increase the performance of your optical plane by increasing the data flows by moving more data across that spectrum. Currently, we can move 240 gig across a 100 gig transport, and that's without dropping packets today. Layer 2 equipment has leveraged this technology for 20 years or better. Okay, and however, within that layer 2 function, there's a great deal of idle packets, especially at the Ethernet level. So you have your idle packets, you have your inter-packet gaps, you have air packets on a per flow basis, and all that actually decreases your bandwidth. So it's very, very inefficient at the layer 2, layer 3, and layer 1 as the transport. So by allocating bandwidth for channels, validated statistical intelligence combines input traffic to maximize channel efficiency. So if we look at a typical flow of data across a time division multiplexing, you can see the multiple flows of data here on the right and left-hand side. And then you can see as the data comes across, you have data, idle packet, inter-packet gap, data, and then on a per flow basis. So you really have a very, very inefficient use of your optical technology. And by integrating statistical multiplexing, we're able to take all those inter-packet gaps, all that idle traffic, and move that more efficiency across the optical plane. And so we get 100% efficiency of data on a per port, per flow basis. And we're doing at the layer 1 port level. So when we look at the percentage of traffic users, you have multiple priorities or 4 priorities of traffic flows within statistical multiplexing. You have your highest priority, which could be a layer 0 or layer 2, layer 3, layer 4. And all those will provide a percentage of bandwidth usage across that optical plane. So you can set percentages on a per flow basis to be 25%, 50%, 75%, or 100%. And the deficit weighted round robin algorithm will allow that traffic to flow on a percentage basis per port, per user. we have, obviously the analyzers of traffic patterns. The algorithm itself looks at all the traffic in parallel. So nobody's getting a scheduling or any type of things. Everything's done in parallel on a per port basis. So with the classifications, we have, the 100%, the 75%, and the 50%, but all those are looked at equally across the entire optical plane. And the data flow moves from 100% to 25% as on a per class priority. So you would have your lowest class at 25%, you would have your second class at 50%, third class at 75%, and then 100% would give you 100% of the bandwidth on a per flow basis. And that's where we're at. Questions?